Hi everyone, Dr. P here, and in this video we'll take a look at chemical equations. Now I've talked a little bit about chemical reactions in lab and drawn some chemical equations, but let's take a look at what a chemical equation is. Basically, they are depictions of chemical reactions. And I'll abbreviate reaction with RxN. So reactions is RxNS. So let's take, for example, the combustion of methane. So I have CH4 gas plus O2 gas react to form CO2 gas plus H2O gas. Now, right now, I've written it unbalanced. Okay, because a chemical equation is like any other kind of equation where the two sides have to be equal to each other. Specifically, these two sides are our reactants and our products. And we have to remember the law of conservation of matter, the law of conservation of mass. So matter is neither created nor destroyed in a chemical reaction. So all of the atoms that we have in our reactants must be accounted for in our products. So I have a carbon in my reactants in methane, CH4, and I have a carbon there in CO2. I have 4 hydrogens here in my reactants, but only 2 in my products. So I'm going to have to adjust this, or balance the chemical equation in order to get all of those atoms balanced. And as I've mentioned in lab, we will also put in parentheses right after a particular compound, we'll put the state that it's in. So this could be a solid, a liquid, a gas, aqueous. So let me just write here, possible states. I always have trouble drawing those Q's. Anyway, we could have a solid, a liquid, a gas, or aqueous, which is dissolved in water. All right, so how are we going to balance this equation? So at this point, we'll balance equations and I'll abbreviate that as Chem EQN. We'll balance chemical equations by inspection. And balancing by inspection is really a fancy way of of saying we're going to use trial and error. All right, so let's take a look then at our reaction of methane with oxygen here, or combustion of methane. So I have CH4 gas plus O2 gas react to give me CO2 gas plus H2O gas. All right, So let's take a look at this, and what I want to do is put in coefficients in front of these compound formulas in order to make the total number of atoms of each element balance on either side. Now, we're not allowed to change any of the formulas. We're not allowed to change the subscripts in the formulas. The only thing that we can change is the coefficients. So what I like to do is I like to start with something that is just in one place on one of the sides, or hopefully both of the sides of the equation. And usually I'll also look for something that's all by itself, and I'll save that for last. So looking at this chemical equation, I'll save the oxygen for last. So I'm actually going to start with the carbon. I have one carbon here in my methane, and I have one carbon in my carbon dioxide. Carbon is already balanced. Next, let's do hydrogen. I have 4 hydrogens here. I only have 2 in my water, but if I put a coefficient of 2 in front of my water, now I have 2 times 2, 4 hydrogens on this side, so those balance. Now I have 2 oxygens on my product side. On my reactant side, I have 2 plus another 2 times 1 gives me 2, so that's 4. So I'm going to need 2 oxygen molecules in order to get that to balance. Okay, I think I should do a couple more balancing examples here, just because it can be helpful. I kind of like some of these combustion reactions. So let's look at the combustion of octane, C8H18 plus O2 gas reacts to give CO2 gas plus H2O gas. So octane is a major component in gasoline. That's where we get the term octane rating from. So let's try to apply the same sort of methodology we did with the previous example. So I'm going to start with my carbons. I have 8 carbons here, and I have just 1 in my CO2, so I need 8 carbon dioxides. All right, I have 18 hydrogens here. I have 2 in each water molecule, so I need 9 waters. Now that I have 9 waters, that gives me 9 oxygens, and then I have 8 times 2, 16 oxygens, so 9 and 16 is 25. So I would need 25 halves, or 12 and a half oxygen molecules. Now that is not ideal. So it's better to, we're going to just multiply everything through by 2. And that will give us 2 octanes plus 25 oxygens react to give 16 carbon dioxides plus 18 waters. So really we're trying to avoid using fractions. We're going to try to avoid using those fractional coefficients. Okay. Let me just adjust the brightness there. That should look a little better. Okay. Now we can do other examples that aren't, for example, that are not combustion. So let me just take a couple from the practice problem set. So let's go ahead and try, let's try this one here. Maybe I'll do it in a different color. So PbNO3 2 aqueous plus Na3PO4 aqueous react to give Pb3PO4 2 solid plus NaNO3 aqueous. All right. So let's see. Let's start by, maybe I'll try balancing my lead first. I have 3 leads here, so I should have 3 over here. That's good. Now I need to balance my phosphate. Notice I said balance my phosphate. Why did I say that? Well, I see I have PO4 here. Do I have phosphorus anywhere else? No, I don't. Do I have oxygen anywhere else? Yes, I do, in the nitrate ion. But I also see I have nitrate over here. So sometimes you can group together atoms if they are in polyatomic ions and the polyatomic ions don't change. So my phosphate is phosphate on the reactant side and it's a phosphate on the product side. Nitrate is nitrate on reactant, it's a nitrate on the product side. So I can sort of treat those as entire groups, in which case with 2 phosphates I'm going to need 2 sodium phosphates. So now I have Pb3, 3 Pb's. That's good. I have 2 phosphates, That's balanced. So now 3 times 2 gives me 6 nitrates, and 2 times 3 gives me 6 sodium, so I would need a 6 here, like so. All right, let me see if I had any other kind of fun ones here. One more because it seems easy. So we will do europium, EU solid, plus hydrogen fluoride, nasty stuff, gives EuF3 solid plus H2 gas. Okay. Well, I'm going to keep my europiums the same on both sides. I have one here, I have one there. We'll go with that. Now, if I have 3 fluorines here, I would need a 3 in front of my HF. And now I have 3 hydrogens, so I should have a 1/2 in front of my hydrogen. But again, we like to avoid doing that. So let's just go through and multiply everything through by 2. And I'm just going to do it right here. So we'll cross that guy out, and that becomes a 6. I have a 2 there, and then that just becomes a 1. And that was not 1/2. I'm sorry. 3. It was 3 halves. So that just becomes 3. I'm sorry. It wasn't half a H2. It was 1.5 H2s. The great thing about balancing equation problems is that you can check your work pretty easily. 2 europium, 2 europium. 6 hydrogen, 3 times 2, 6 hydrogen. 6 fluorine, 2 times 3, 6 fluorine. And there we go. All right, well, definitely practice that. There'll be some of this on the next class activity. And I do want to mention what these chemical equations represent. And that is, let me go back here to my reactants and products and our balanced equations. We get a lot of information. Of course, we get what the components are, what the reactants are, and the products. We get what states they're in. But most importantly, we get our relative numbers of atoms and molecules at the microscopic scale, the nanoscale, or relative numbers of moles of compounds and elements at the macroscopic scale. So these coefficients, so if we don't see a coefficient, that's a 1. So the 1, the 2, the 1, and the 2, they represent both, one molecule of methane reacts with 2 molecules of oxygen to give 1 molecule of CO2 and 2 molecules of water. Or we can say 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of CO2 and 2 moles of H2O. So yes, I know we didn't start out talking about moles, but these guys have a way of creeping up into everything. All right, I'll talk more about moles and chemical equations in the next lecture video. But until then, stay safe out there. Bye now.